Today we will deal with some problems on Biot Savart's law. In this lecture, which is denoted by lecture 3b, in earlier lectures we discussed about magnetic induction, Maxwell's second equation and Biot Savart's law. Let me start with a question, a specific email inquiry. Why does Farad and Henry come into the expressions of E and B respectively? At the very outset, let us mention that vector E, which is the electric field, has unit volt per meter, and vector B, which denotes magnetic induction, has unit Tesla, and this was discussed in lecture 1a. Let us now see how Farad and Henry they go into the expressions of E and B. Let us start with Coulomb's law first, and this is Coulomb's law. And if we write down the explicit expression of vector F, we have this one, and we are not bothered about the direction of vector E, which is along r cap, so we have r cap on both sides, and therefore we have 1 by 4 pi epsilon 0 expressed as E r square by q prime. Q and q cancels out, and if you put the units, we'll end up with volt per meter for E, meter square for r square, and coulomb for q prime. So supposing that we do not know the unit of 1 by 4 pi epsilon 0, we have 1 by 4 pi epsilon 0 expressed in terms of meter, and in the denominator we have coulomb per volt, which follows from this expression. Here C is for coulomb. Again we note that charge can be expressed as a product of capacitance and potential, that is Q equal to CV. So capacitance can be expressed as charge by potential, and if we put the units correctly, then we end up with coulomb per volt, and this combination of units is referred to as farad. Now this coulomb per volt occurs in the expression of 1 by 4 pi epsilon 0 here in the denominator, and therefore 1 by 4 pi epsilon 0 can be recast as meter per farad. So we have 1 by 4 pi epsilon 0 as meter per farad, and therefore epsilon 0 turns out to be farad per meter. We will sum up later, but first let us consider the Lorentz force equation, which is F equal to Q into V cross B, and instead of B we will put this expression which we obtained from Biot Savart's law that was discussed in lecture 3a. And therefore if we take mu 0 by 4 pi to that side, to the left side it becomes 4 pi by mu 0, and we have this expression. We can write this in a crude form to get an estimate, and we end up with this relation. Here let us check a bit. I prime dr prime is here, r cap by r square. Here we have 1 by r square, this having no unit, and qv is there, and F is the force. So in the next step we can put the units, and assuming that we do not know the unit of 4 pi by mu 0, we end up with this relation after a bit of simplification. Now here we have coulomb per second in the numerator. Coulomb per second means ampere, and therefore 4 pi by mu 0 turns out to be ampere square per Newton, and 1 ampere can be taken down, and therefore it can be recast as ampere, and in the denominator we have Newton per ampere. Now the expression for Tesla which we obtained in lecture 1a was this one, Newton per ampere per meter, and therefore this Newton per ampere can be written as Tesla into meter. If you multiply this right hand side by a meter by meter, then we end up with Tesla into meter square per meter, and Tesla into meter square is actually Weber, which we discussed in lecture 1a, Weber being the SI unit of magnetic flux. So what we have essentially done is, in the expression for 4 pi by mu 0, we had a Newton per ampere, which turns out to be Weber per meter, and therefore we can replace it here. So 4 pi by mu 0 can be written as ampere into meter divided by Weber. Let us now recall an expression that connects magnetic flux and current, and this will be done in a class on Faraday's law. The magnetic flux, as we discussed earlier, is given by the surface integration of magnetic induction. According to Orsted's experiment, current produces a magnetic field, and from this expression it follows that if B increases, then phi m will increase. So in a nutshell, we can say that if I increases, then B increases, which again forces phi m to increase. So I and phi m are proportional, and therefore we can write the proportionality in terms of this relation, where the proportionality constant is inductance. So let us put the units in phi m equal to Li expression. Weber is the unit of phi m, the magnetic flux, ampere is the unit of current, and inductance has unit Henry, and therefore we have Henry expressed in terms of Weber per ampere. Now this we can put in the expression for 4 pi by mu 0, which we got to be this one, and therefore Weber per ampere is Henry, and therefore 4 pi by mu 0 is meter per Henry, which gives mu 0 as Henry per meter. Let us now sum up. This is Coulomb's law and this is Biot Savart's law. The question was, how does Farad and Henry intrude into the expressions of Coulomb's law and Biot Savart's law? Or in other words, how does Henry and Farad occur in the expression of B and E? So the straightforward answer will be Farad occurs into the expression of E in the proportionality constant, and Henry has a place in the proportionality constant in the expression of magnetic induction. So this is how Henry and Farad, they occur into the expressions of B and E. Let us now, as promised earlier, discuss a bit about the famous scientists Biot and Savart. Now, Biot lived on Earth for 87 years. He was a son of a treasury official. He was a French, and he was a physicist, mathematician, cum astronomer, having special interest in optics and magnetism. Biot served in artillery and later on served as professor, and his works involved those on meteorites, and he was the one who first traveled in a hot air balloon, and his co-passenger was the famous Gay-Lussac, and this he did to measure Earth's magnetic field with height. Now Biot in 1820 discovered, or rather gave, Biot Savart's law, and he was helped by his colleague Savart, who was the son of an engineer who lived on Earth for 50 years, who was a French. He was a physicist, mathematician, having special interest in acoustics, and works of Savart. Some of the works of Savart were to determine the range of human hearing and music related research, and he loved violin also. It is now time to do some problems relating to Biot Savart's law. In the earlier lecture, lecture 3a, we discussed about Biot Savart's law, and here it is. Now based upon this Biot Savart's law, we'll try to find magnetic induction for various cases. Let us first take up the case of arbitrary plane curve C prime, which is here, A and B being the extremities of this plane curve. It is a plane curve means it lies in a plane. A plane can be described, or a phenomena in a plane can be described either by using xy coordinate system, that is the Cartesian coordinate system, or by using plane polar coordinate system. This is the xy plane, x-axis, and this is the y-axis. P is the origin, and we have considered a point M whose Cartesian coordinates are xy and plane polar coordinates are r and theta. And this is the unit vector along the direction of increase of the radial coordinate r, denoted by r hat. Now, in our problem, we have denoted this small r by capital R, and therefore we have this diagram. So capital M is a point whose radial coordinate is capital R, and the plane polar coordinates are r and theta, r being capital. So it's the same diagram, just for convenience, for future convenience, instead of small r, we have used capital R in view of Biot Savart's law, because in Biot Savart's law, this capital R has a special significance, it being the position vector of field point with respect to the source point, as indicated in this diagram. Now this is the source circuit, of which I prime vector dr prime is a source current element which produces a magnetic induction at the field point P, whose coordinates are in spherical polar coordinate system, small r, theta and phi, and this being the position vector with respect to origin O, which is 0 0 0, and this is the capital R vector, which represents the position vector of field point with respect to the source point. Now for future convenience of understanding, let us redraw this circuit just by drawing this portion. So we have just picked up AB portion and placed it here, other things remaining same. So this is the I prime dr prime as before. And another change we make is we take the point P, instead of here we take the point there. So this is P point. For all other things remaining same, let me explain it a bit. This is the origin O, with respect to which this is the field point having spherical polar coordinates are theta phi, and the most important length that appears in Biot Savart's law is this length, which is let me repeat, it is the position vector of the field point with respect to the source point, and we can write down the Biot Savart's law, and this is Biot Savart's law. Now let us study minutely. In Biot Savart's law we have an r cap, and r cap is this one. So it is a unit vector from M to P, and therefore let us rewrite it in the following way, where everything remaining same, we have only written MP hat, because the direction is from M to P, from source to field. So instead of r cap, let us write MP cap, just for future convenience. So this is Biot Savart's law, M being the source point, P being the field point, and here the unit vector is from M to P. Now the problem we are studying here, in that problem we have again redrawn it. AB portion has been redrawn here, and this point P is here. So everything is same between these two diagrams, only that in this situation the origin is shifted and placed atop P. So P is the origin firstly, and secondly this direction has been defined, not this direction. So this direction is called r cap. So this is the diagram, have a relook into it. So this is the circuit under consideration, source circuit, a portion of which is I prime vector dr prime at point M. This is the source point, and P is the field point, but now P is the origin, and this is the radial unit vector, so it is r cap. Now in Biot Savart's law we have MP cap, so in Biot Savart's law we have to put, instead of r cap we have to put MP cap, which means it would be minus r cap. So we have rewritten Biot Savart's law here. So in this problem, when we will write Biot Savart's law, we will just write in this way. Now this is the problem under consideration. We have gone back to this problem with a little bit of elaboration regarding the position of the field point and the source point. So let us restart. This is AB, the planar wire denoted by C prime, and PS is the reference line, which is the polar axis, or it is the reference line, and ML is a small portion of AB, it representing the source current element. And the equation of AB can be taken to be RF of theta, where theta is the angle which this PM makes with the reference axis. So this is the theta angle. PM makes an angle theta with the reference direction PS. To proceed further, we have to do a small construction, and that construction is at this point M, where its coordinate is r, polar coordinate is r, let us draw an arc, a small arc of amount d theta, so that we end up with Mn. So Mn is the arc. Now since this is r and this angle is d theta, so the length of Mn arc is obviously r d theta. And Pn and Pm, that is Pm and Pn, are both capital R, because we have drawn an arc of radius r. So this is the radius of the arc, this also is the radius of the arc similarly, so these two lengths are same. So in a sense we have an isosceles triangle here. Isosceles triangle, it has two sides equal and the base is Mn. Again we note that the value of d theta is as small as we please. It is extremely small, it tends to 0. It is as good as 0. We cannot define d theta. We cannot define d theta in such a way that it differs from 0. It is always 0 in the limit. Now sum of three angles of a triangle is 180 degrees, and if it so happens that one angle is as good as 0 or as close as 0, then this automatically implies that the sum of the other two angles will be 180 degrees, and therefore it being an isosceles triangle, these two angles, the base angles, are equal. So this is 90 degrees and this one is also 90 degrees, and therefore we can take in the limit Pmn is 90 degrees. Now PML, this angle PML, this angle, let us call it phi, and again this is 90 degrees, which means the angle NML is phi minus 90. So as is indicated, we have also mentioned the value of this angle. The task is to write down Biot Savart's law and then how the work is done. And this is Biot Savart's law. We have earlier explained that when we write Biot Savart's law in this case, MP direction or the unit vector along MP will come into the picture, and here MP is minus of this direction. So we have this one as representing the Biot Savart's law. So the task is to perform a cross product between dr prime and r cap. Minus can be taken outside, and the second one is to perform an integration. In other words, we are very close to the final result. Now a cross product means a sign will come. So we have to see the diagram and find what is the angle between vector dr prime and r cap. Minus sign has been taken outside and written here. So essentially we are taking cross product of vector dr prime and r cap. So this is vector dr prime, this is r cap, this is the included angle. Now this entire angle is pi, this full angle, it's a straight line, and at any point on this straight line we have a pi angle on one side. So this is pi, and this angle is phi, PML is phi. So in other words, this angle will be pi minus phi. So this angle, the angle between vector dr prime and r cap prime, is just pi minus phi. So I prime dr prime, apart from these constants and a negative sign, within the integrand we will have I prime dr prime, sine of the included angle which we showed to be pi minus phi, and r cap, its mod is 1, and if you take a cross product, this is I prime dr prime and this is r cap. So if you take a cross product, we'll end up with a direction which points into the paper away from the reader, so that if n cap is the unit vector pointing towards the reader, after taking cross product between these two vectors, the resultant direction will be minus n cap, and that is what we have written over there. So this is the result of cross product between these two factors, and therefore a simple rearrangement, namely minus minus is plus. So we have n cap here, mu 0 by 4 pi, I prime is a constant current flows through this wire, and therefore I prime can be taken outside, and we have simply dr sine of pi minus phi is sine phi r square. So we end up with this result, and the extremities of the wire, A makes an angle theta 1 while B makes an angle theta 2 with the reference axis, so that the integration is over C prime, that is from A to B, that is from theta 1 to theta 2, as has been indicated over here, theta 1 to theta 2. Now the final step is to make it even simpler, because we are to integrate from theta 1 to theta 2, that is angle theta should be there, or everything should be written in terms of r, the limits. Let us now consider this triangle NLM. Let us consider the triangle NLM. Now MN is an arc, so it is a curved one, but the amount of curvature is extremely small because d theta is as good as 0. So this is actually a straight line in the limit, and therefore NML, this triangle, can be redrawn here, and this is 90 degrees, so this one is 90 degrees, this being essentially a straight line. We have a right angle triangle here, so NML, so this is the right angle triangle where this is 90 degrees, and NML is phi minus 90 degrees. Now we can study this triangle and find the value of cos of this angle. So cos of NML, or in other words cos of phi minus 90 degrees, is, now what is cos? Cos is base by hypotenuse. The base is, this one is the base. If this is the angle under consideration, then this is the base, this is the perpendicular, this is the hypotenuse. So being a cos, here we have base by hypotenuse, so instead of base we will write Mn, and hypotenuse is obviously Ml. Now Mn we have written earlier, Mn is Rd theta, so we can write it, instead of Mn we can write Rd theta. And what is Ml? Ml is simply dr prime, so we have written here dr prime, and therefore here also we have dr prime, because here we had dr prime, so here we will have dr prime, and what we get is dr prime sine phi is equal to r d theta. This is what we get, and dr prime sine phi is here, and we can place therefore for it instead of it r d theta, and therefore the value of vector b at p turns out to be of this value, and one capital R and the other one in the denominator cancels, so that we get the final result. So b at p is this one, where integration is to be performed from theta 1 to theta 2, from theta 1 to theta 2, here is theta 2, that is from a to b. So the arbitrary plane curve produces this amount of magnetic induction at the pole. This is also called pole. So P has three characteristics. It is a pole, it is an origin, it is the field point. Using this result, we can deduce other results, like finding the magnetic induction in a circular circuit at the center. So this is a circular circuit carrying current I prime, and this is the current element, this is the distance, this is the field point, this is the source point, and this is the reference line, and with respect to the reference line, this representative point or typical point has angle theta, and we can use the result that we deduced for an arbitrary plane curve, current carrying curve, that is this result. And in this expression we have one theta 1, one theta 2, and as is evident from this diagram, the point A, which corresponded to theta 1, is now 0. Theta 1 is 0 here, and then you move throughout the entire circuit and come back to point B, which is actually the same point as that of A, and B makes angle with the reference axis of amount theta 2, which is in this case, since you traverse the entire circle, full circuit, it will be 2 pi. So in the expression that we got for an arbitrary planar circuit, we have to substitute 0 for theta 1 and 2 pi for theta 2, and then we get this expression where we have integration from 0 to 2 pi, which turns out to be 2 pi, and therefore if we substitute it here, this is the result. So for a circular current carrying loop, the magnetic induction produced at the center will be of this value. Here n cap is a unit vector that is pointing towards the reader away from the paper. Let us now consider the elliptic circuit as shown here, which carries current I prime, and this is the source current element, and this is the field point, and R as before is the position vector of the field point with respect to the source, and PS is the reference line, and with respect to this reference line, this representative point, that is this R, makes an angle theta. Now the general formula for arbitrary plane curve was this one, which we obtained, and this can be applied here. Now two modifications are to be made in the general formula. We should remember that this was the reference line and the starting point of the circuit was A, so that PA made an angle theta 1 with the reference line. But unlike this situation, here A lies on the reference line, so that theta 1 is 0. So when we apply this formula here, we have to put theta 1 0. Now if we move around the entire circuit along the ellipse, and then we come back to the initial point, which means theta 2 is a full circuit, that is 2 pi. So these are the modifications that are made. The second modification regarding limits, the second modification is what is the value of 1 by r. Now it being an ellipse, we can use the polar equation of the ellipse, which is this one, 1 plus epsilon cos theta by L, where here P is the focus of the ellipse, which is also the field point, which is also the origin, and here A is this length, which is called semi-major axis, In this formula we have an epsilon, and this epsilon is the well-known eccentricity of the ellipse, which happens to be lying between 0 and 1, and L represents the semi-latus rectum, and L is related to eccentricity and the semi-major axis through this equation. Now, these are standard equations which we are using. So this formula with these substitutions take this form, where theta 1, instead of theta 1 we have 0, instead of theta 2 we have 2 pi, and instead of 1 by r we have 1 plus epsilon cos theta by L. Now L being a constant, for a particular ellipse, epsilon is a particular value lying between 0 and 1, so it can be taken outside the integral sign, and therefore we have this integral. Now it's very easy. This integral has two parts. Now this one turns out to be 2 pi, and here we have epsilon is constant, it goes outside, and here we have just 0 to 2 pi cos theta. Now this is a sinusoidal function, and we are integrating, it's a periodic function, sinusoidal function, integrating over a full period, which means it gives 0. And therefore collecting all the results, we have this as the magnetic induction at the point P created by this elliptical circuit, which carries a current I prime. And the unit vector is as before towards the reader, away from the plane of this paper. Let us study another application of this formula, where we are considering a parabola. So this is a parabolic circuit which carries current I prime. The current is coming from infinity and then it goes back to infinity. So the arbitrary plane curve which started from A and which ended at B, now in this case A is at infinity and so is B. So here too we will have theta 1 0 and theta 2 2 pi. This point is coming from a very large distance, so the angle with the reference axis is 0, and it again goes to a very large distance, which means after a full circuit. So making a full circuit means you are going by an amount of 2 pi, so theta 2 is 0. So here too the integration is as before. In the case of circle and ellipse, we have theta 1 to theta 2 being replaced by 0 to 2 pi, and as in the elliptic case, here we have to replace by its polar equation. Now the polar equation of a parabola is the standard one, where P is the focus, it's the field point, it's the origin, V is the vertex, and this distance between V and P is A. So substituting the polar equation in this formula, we get in the integrand 1 plus cos theta by twice A instead of 1 by r. Now it becomes very easy. It dissolves into two parts. One is 0 to 2 pi d theta, which is 2 pi, and this one is as before, it is 0, and therefore collecting all the components, we end up with this relation. Here let me again re-emphasize that A is the vertex to focus distance, that is the distance Vp. We can use this formula for calculation of magnetic induction at the center due to a semicircular current carrying circuit. So this is the semicircular current carrying circuit, and we have written down that formula, we have copied the formula. Now in this situation, theta 1, it starts from A, so theta 1 is 0, and now we are not making a full circuit but we are making a half circuit, so this angle is to be taken care of. So theta 2 here is pi. So the integration is to be carried from 0 to pi d theta, and therefore after integration we end up with pi, so that for semicircle the magnetic induction at the center is of this value. And as before, the unit vector or the direction of the magnetic induction is towards the reader, it's away from the plane. So let's make a gist of what we did till now. We first considered an arbitrary plane curve and calculated the magnetic induction due to it at the pole, which turned out to be of this value, and this circuit, this formula was used to evaluate magnetic induction for other circuits like a circle, like an ellipse, like a parabola, like a semicircle. Now in all these cases, one thing is common, that is the direction of magnetic induction. It bears a right-handed screw relation with I prime. It bears a right-handed screw relation with I prime. That is to be noted here. In the next lecture, which will be called 3C, we will evaluate the magnetic induction at any point on the xy plane which, or rather through which, a straight wire passes, which is of finite length. And we will also calculate the magnetic induction at point P by this type of circuit, which consists of two arcs and two straight portions. And also what will be the magnetic induction at the center of a square loop as well as at the center of a hexagonal loop, and plus some other problems will be addressed. Also, we'll evaluate the value of magnetic induction due to a circle starting directly from Biot Savart's law. In this lecture, we did not do it straight. We used a formula for an arbitrary plane curve. But in the next lecture, we will do it directly from Biot Savart's law. Let me end with a quote by American singer and multi-instrumentalist Angelo. When solving problems, dig at the roots instead of just hacking at the leaves. In our case also, we have to sever, slice and dig deep to get to the root. In other words, we should treat any problem to be at our mercy. Only then we can win over the problem. Thank you.